4.3c, part 1. So this little chart right here is going to be like your dictionary for this section right here. Okay, reference it if you need it. This is going to tell you and help you understand, because we are going to be looking at graphs of the function, graphs of the derivative, and graphs of the double derivative. And we're going to use that to analyze things about the entire function. Okay? Each one of those graphs tells me different things. Each one of those graphs has different rules, and intercepts mean different things. So as you look at the different graphs, because remember, it's the derivative and then the derivative of the derivative. That's going to give us different information about the function. So, of course, I know you all know how to analyze a regular function. You can find the zeros, you can find where the function is positive, and you can find where the function is negative. Okay, I think everybody in here can do that with a regular function, right?
Yeah.
That's algebra 1, algebra 2.
I can.
Good. So, then we have the derivative. So the derivative, the x-intercept acts as the max and the mins when we cross the x-axis. That's because the derivative is the slope of the function. So if the slope goes from negative to positive, we know that we have a max or a min if it goes from positive to negative, negative to positive. If we go from a positive slope to a negative slope, we have a maximum. If we go from negative slope to a positive slope, we have a minimum. Okay, so keep that in mind. I usually draw it out with the little arrows every time just to refresh my memory. If the graph of the derivative is above the is above the x-axis, we know the function is increasing because it's a positive slope. We know that if the graph of the derivative is below the x-axis, it's decreasing because it's a negative slope. And then lastly, the double derivative. So the points of inflection of f of x are where the graph crosses the x-axis. The function is concave up when the double derivative is greater than 0. And that would also mean the second derivative, or the first derivative, is decreasing. And then we're concave down when the second derivative is greater than 0. Okay. So, first example we'll look at here is just analyzing this graph. So first thing you always want to do when you're asked to analyze one of these, to find all these features, you want to first determine which graph they give you. So they're either going to give you the function, they're going to give you the first derivative, or the second derivative. Each one of those are going to tell us different things about the graph. So here they gave us the derivative. So keep in mind this is the slope of the function, graphed. Okay? So, to determine where the function is increasing, we know the function is increasing everywhere that the slope is what? Positive. So everywhere that the slope is positive is going to be everywhere that it is above the x-axis. So that's going to be from b to 0. And just a reminder of algebra 2 stuff, anytime we do increase, decrease intervals in math, you always use parentheses, never square brackets. And the reason for that is the derivative is greater than 0. So for the next one, we know that the function is decreasing everywhere the derivative is what?
Less than 0.
Negative, less than 0. So it's decreasing from
A to B.
A to B, where else?
0 to 8. 0 to 8.
0 to h. Okay. And that's because the derivative here is less than 0. It's tricky because if you think of this as the function, it's all different. So you remember, this is the derivative, not the function. Okay? All right. Next one, we're going to determine where we have a maximum and minimum. So we know that maximums and minimums occur when the derivative goes from positive to negative or negative to positive, which occur here and here, right? That's the two spots where we change sign of the derivative. So everybody see that? Okay. So this one right here goes from negative to positive. So negative to positive looks like this. That creates a what?
Minimum.
A minimum. So we know we have a minimum at x equals b. And over here we go from positive to negative, which means we have a maximum at x equals 0. And that's because the derivative went from positive to negative, and this one's because the derivative went from negative to positive. Make sense? Like I said, it can be tricky to think about.
So far, I understand it.
Good.
And that, yeah, that's just so far. It's positive.
So I'm gonna erase everything we have on here just because I want to make sure you guys don't get confused with anything I already have written. So next one is concave up. So concavity is based on what in general? It's based on the first derivative, second derivative, or the original function.
Second derivative?
Yeah, we use the concavity test, we use the second derivative, right? So the second derivative compared to this would be the slope of this function. This is the slope of the derivative, right? Slope. So we're looking at, now we're going to look at the slope of this function, okay? So it's going to be concave up everywhere the slope of this is positive, which is here, here, and here. That's concave up. Concave down is where the slope of the derivative is negative. So we're concave up from A to C, and then D to E, and then G to H. And then we're concave down from C to D and E to G. And that's because slope of is positive, and then slope is negative. So any questions so far about what we have? And we know that points of inflection occur where concavity changes. So wherever concavity changes, we know that points of inflection occur.
C, D, G.
Exactly. So our points of inflection are here, 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 and here. Okay. So at x equals C, x equals D, x equals E, and x equals G. So the reason I put x equals is because technically speaking, a point of inflection is going to be an x and a y. Now the reason we don't know what the y coordinate is the y coordinate of the point of inflection is going to be based on the original function, right? Now, even despite the fact that we don't know what the y values are on this, we could technically estimate. But the problem is, points of inflection, we're talking about the actual function. We're using the other derivatives as a tool to help us find them, but we don't know what the y coordinates on the function are. So if we had the function, we could plug the x's back in and get the y, but we don't. So we just simply, that's the only information we know about them. Okay? So that makes sense to everybody? If I gave you a function, you could of course find them though. All right.
Can you go back?
Yeah, sure.
Thank you.
Mm-hmm. Oh, what's happening? It just got stuck. You know.
Yes.
Okay. All right, so for the next one, keep in mind, we're no longer looking at the derivative. What are we looking at?
Second derivative.
The second derivative. Now, this is not necessarily the same function or anything like that, so keep that in mind. This is a different function. We're looking at the second derivative, so we're looking at the derivative of the derivative. So this is going to be interpreted differently, okay? So we know that concavity occurs when the second derivative is what? Positive. Concave up occurs. We know that concave down occurs when the second derivative is negative.
What's the point of doing second derivative then? I mean,
To
like,
find concavity.
Do we not find it here?
The point is depending on what they give you, we have to be able to analyze it differently, right? So on this one here, we know that it's concave up everywhere that this is positive, which is here and here. And it's negative here to here. So I'm just going to identify those. So it's concave up from -3 to -1, and then from 4 to positive infinity. Good. it's concave down from negative infinity to negative 3, negative 1 to 4. Okay. So, point of inflection. Points of inflection occur when the concavity does what? Changes. So it just so happens when you have the second derivative, typically when you have the derivative of the thing you're analyzing, it's going to occur at the intercepts. Okay, because that's where things change, right? So we have a point of inflection here, here, and here. So when the second derivative changes sign. Does that sound familiar to you all when you make those number charts? When we change sign, that's a point of inflection. Same thing. You're seeing it visually now. It's the same thing. Okay. Next one. You need a pencil or something?
No.
Oh. So this is where things can be a little bit tricky. Here we are going to actually make a sketch of a graph using information provided to us. So what can make this difficult is with a sketch sometimes, if you draw a sketch, you may have to erase certain parts of it. So I recommend doing this lightly in pencil every time so you can adjust things as necessary. Okay. So step one, when you're sketching a graph, they're going to give you some just coordinates. That's easy. Everybody knows how to do that. So we're just going to start by plotting the coordinates that they give us. So we're just plotting coordinates right now. So we got that one done and out of the way. Now the problem with the other ones that makes it particularly tricky is you can't always do these in this order because there's going to be multiple things being asked of you about each interval, correct? So let's just go through and explain what each of these mean to everybody. So the derivative is less than 0 when x is less than 3. So what that means is we know that everywhere less than 3, I should make a bigger marker here so you can see it better. It's not going to take me 20 minutes to do. I swear I just made it bigger and it didn't get any bigger. I don't know. But everywhere here, okay, everywhere in this region of the graph, my slope is going to be negative. So what this means is slope is negative. Okay, slope is always negative when the derivative is less than 0. Okay, from here to here, my slope is what? Positive. So slope is going to be positive from everywhere that's greater than 3. Okay, that's what I know so far. So if that were the only requirement, you could graph this right now, down and up. But there's not. There's more requirements. There's also requirements about the concavity as well, because we start talking about the second derivative, we know it's concavity. When concavity, or the second derivative, is less than 0, what does that mean about the function? Concave what?
Down.
Concave down. So,
I didn't know that.
it's concave down whenever the second derivative is less than 0.
Oh, so slope is negative. You know, it's less than 0.
Yes.
Okay.
Exactly. So concave down is everywhere from here to here. So from here to here, we know we need to be concave down. And then the last requirement is that we have to be concave up on these intervals. So concave up is from negative infinity to 0. So that's a lot of stuff. That's this whole section over here, right? We're going to be concave up over here. And we're also going to be concave up from 2 to positive infinity. So you don't really need to do the highlight. I mean, it helps you kind of visualize what's happening, but it just kind of helps you understand all the rules and regulations. Now, over on that side of the board, I just did that, but it just tells you what each of those look like. Okay, concave up, concave down. So, concave up looks like this. Okay. So something is concave up when it has this appearance to it. Okay. Concave down has this appearance to it. Okay. Now with concave up, Okay, this is concave up when the slope is negative. This is concave up when the slope is positive. This is concave down when the slope is positive. This is concave down when the slope is negative. Okay, so let's go ahead and graph it. So in this region right here, we need to have a negative slope and be concave up. So that's going to look something like this. Concave up and the slope is positive. So I maybe didn't draw it like pronounced enough, but it's kind of hard to do so on here, so I'm trying my best to show you how it's concave up as well. In this region right here, we are going to have a negative slope, but we're going to be concave down. So that's going to look like this. So do you see the difference between, while the slope is still negative for both of those, do you see how the concavity has changed?
X squared.
Yes.
That looks like.
It looks like x cubed.
That's what I meant.
Mm-hmm. Okay. So for this piece right here, it's pink and yellow. So we have to have a negative slope and be concave up. Okay.
I think I did it.
So concave up and negative slope. That's going to be like this. Okay. And then the last section over here is slope is positive and we're concave up. And then we need to go back and do this side. So it's just a continuation of this right here. So concavity is now something extra you've added into just the aspect of slope. So if anybody does eventually want to take a picture of the little rules up there, it might help you. It just helps you understand what the concavity looks like. All right. So next one, this is the last one we're going to look at for today, and then we'll continue tomorrow. So example 4 is we're going to determine where all of these things occur. Which graph are we looking at right now?
You're looking at your first derivative?
The first derivative. So remember, just keep in mind what you're looking at. That's going to tell us how things go. Okay? So we want to know where the function is increasing and decreasing. We know that the function is increasing when what? When the slope is what?
Positive.
Positive. So if the slope is positive, we know the function is increasing. So go ahead and find where the slope is positive.
Right there.
Thank you. You're welcome. Yep. So slope is positive here and here, remember, because derivative is slope. So we know that our function's increasing there. And then we know my function's decreasing when the slope is,
Below 0.
yeah. So we don't know what's happening past this because it could like wave back down again. So I'm just going to be safe and say that it's around, I don't know, 1 or 1.5. We'll just say -1. So from -1 until we get to 1, 2, 3, 4, 5. And then 6, 7 to 9 is increasing. And then where is it decreasing?
It's 5 to 6, 7. Yeah.
5 to 7.
Good job, Robert. I'm proud of you.
And then local maxes and mins. So we know that maxes and mins occur when?
At y equals 0.
Yeah, when the derivative's at y equals 0 because the slope changes what?
Side.
Slope changes.
Side.
So here it goes from positive to negative, and here it goes from negative to positive, correct?
Mm-hmm.
Positive to negative makes a
Max.
max. So we know we have a max at x equals 5. And then negative to positive means we have a,
Minimum.
yep.
Those are close.
Alright. So that's it for today. We'll do 5 tomorrow so we don't rush it. You can do